see how it goes. I don't
I
think
think
they
they might miss every project.
I gotta let see you later.
Yeah, I have to, not just like kind of like it.
You're bad.
Maybe at home or something.
Will you add number 9 to the board?
Number 9. Okay, so let's see where we stand with chapter 22. So we formulated the basic rules of electromagnetic induction. So we started with a simple rectangular circuit loop with one side only that is moving with velocity v in this direction and uniform magnetic field everywhere. That is into the board, let's say. And using this setup, we discovered that the Lorentz forces generate redistribution of electric charges in this moving straight piece of wire. And as a result of this redistribution of charges, a voltage difference appears between those two ends of this moving piece of wire. And that voltage difference, induced voltage or induced EMF, we found to be proportional to the speed of this moving piece of wire, proportional to the length of this moving piece of wire. Let's use lowercase l for the length, L, and proportional to the magnitude of the magnetic field. After that, we said, well, this is good, but what if this moving piece of wire has arbitrary shape? And what if it is moving in arbitrary direction? And the magnetic field also is not uniform into the board, but it's also in some arbitrary direction with differing magnitude. And we managed to rewrite this expression in a way that is independent of the geometry, independent upon the shape of the loop, instead of rectangular arbitrary shape, and instead of uniform magnetic field, arbitrary magnetic field in any direction you want. And the result was that the induced IMF or induced voltage is equal to the rate of change of magnetic flux that goes through the plane of the loop. And that loop, of course, can be any shape in space, three-dimensional shape in space. The only thing that matters is, in order to have induced EMF, you need to have changing magnetic flux through the area defined by that loop. After that, we described the direction of the induced voltage and the induced current using, instead of this minus sign in Faraday's law, instead of this minus sign, using description that we called Lenz's rule. So it was quite complicated series of events, but the result was always, you always have to figure out correctly the direction of the induced voltage and the induced current if current is flowing through. After that, we talked about mutual inductance. We have one coil, primary coil, that is energized, so it is connected to some, let's say, AC voltage. So current is flowing in it. Magnetic field is created by this current. And a secondary coil that may be separated from the first one somewhere in space. But part of the magnetic field created by the primary coil enters the secondary coil and creates magnetic flux in the secondary coil. Variable magnetic flux means that it induces voltage in this secondary coil. And if the secondary coil has a closed circuit, is a closed circuit, in that case, you are going to see an induced current. So the total magnetic flux in the secondary coil is the flux, magnetic flux through one loop of the secondary coil multiplied by the number of turns in the secondary coil. So this total magnetic flux, this expression is the total magnetic flux that appears in the secondary coil. That total magnetic flux must be proportional to the current in the primary coil. And the coefficient of proportionality we called coefficient of mutual inductance. We demonstrated that the voltage induced in the secondary coil, the EMF induced in the secondary coil, voltage induced in the secondary coil, is equal to the coefficient of mutual inductance. So this coefficient, of course, only depends upon the geometry, how those two coils are oriented with respect to each other, what is the distance between them, what is their shape, and so on, times the rate of change of current in the primary coil. And there is a minus sign again, but again, the minus sign, we don't use it except we prefer to use Lenz's rule. In a similar manner, if you have one single coil, only the primary coil, and it is energized, so it is under voltage and current is flowing in it, the total magnetic flux that flows through this single coil is going to be proportional to the current that somebody drives through this single coil. The coefficient of proportionality we called coefficients of self-inductance, or just inductance for short. And we demonstrated that the induced voltage, equilibrium voltage that is going to be established in this single coil, is equal to the inductance multiplied by the rate of change, the rate of change of current in this single coil. So those are the equations that we encountered. And well, what is left now is a little bit of discussion about the energy that is carried by electric and magnetic fields, and also some practical applications. So people here want me to solve problem number 9. Keep in mind that the homework assignment is due this week on Wednesday, so we don't have too much time to delay it. Yes?
Can you add number 10 up there as well, please?
Okay, problem number 9 and problem number 10. So before continuing with this discussion, let me show you some simple demonstrations of the induction phenomena. So one simple demonstration would be this flashlight. So this flashlight at the moment is not charged because it doesn't have a battery. Well, it may have some small battery or a capacitor, but it is not charged. But inside it, you have a magnet, permanent magnet, that is able to move with respect to a solenoid, a coil that you see actually. So when you shake it, you move the magnet. This moving magnet induces voltage and induces current in this solenoid. And that current is used to charge a capacitor or a battery. And the result is going to be that without external source of energy, electrical energy, without external source of electrical energy, you have a flashlight that works. So you don't need to replace it with batteries. You just have to convert the kinetic energy, the mechanical energy that you put in with your hands, it converts it into electric power. A similar example is this demonstration right here. So you have a secondary coil that is not energized, but it has incandescent light bulb. Incandescent light bulbs consume quite a lot of electric power. But there is no battery inside. It is just a coil that forms a closed circuit. And now you also have a secondary, here is a primary coil that is connected to the grid. And this primary coil, well, there is some ferromagnetic core in it, iron core, to keep the magnetic field that is created by the current that flows in this primary coil, to keep the magnetic field more or less focused rather than letting it expand all over the room. And now look what happens when I let current to flow in this primary coil. So there is no connection. There is no electrical connection between the primary and the secondary coil. I can even insulate it with some paper or something. Yeah. And you see that. So what is happening is that the current in the primary coil produces variable magnetic field because the current is AC current. And this variable magnetic field induces magnetic flux, variable magnetic flux in this secondary coil. And this variable magnetic flux, according to the Faraday's law, here it is, variable magnetic flux, variable in time, induces the voltage. In the coil, the voltage drives current, and the current lights up the light bulb. So this is exactly how those wireless chargers of your cell phone work. So this is your cell phone. This is the charger. You just put your cell phone on top of the charger, and here it is. Instead of a light bulb, you have it charges some battery in your cell phone.
So variable magnetic field from the machine that you turn on creates variable magnetic flux
Here.
in that.
Mhm.
Then that flux creates
Induces the voltage, and the voltage drives the current, of course.
Which creates another magnetic field of its own.
Yeah, yeah, but we stop here because we don't care that much about the magnetic field that is present now in this secondary coil. We don't care. For practical applications, it doesn't matter. But of course, in other applications, it may. So for this particular demonstration, the magnetic field of the induced current doesn't matter. Now, the direction of the induced magnetic field, though, right? So you have variable AC current here, it creates magnetic field. The magnetic field generates voltage and drives current in the secondary coil. The direction of that current is such that it has its own magnetic field, induced magnetic field, in direction such that to oppose the variation of the magnetic field in the primary coil. And this principle, this Lenz's rule, you can demonstrate it this way. So instead of secondary coil like this, think about secondary coil like this. It is a cord, right? It is one turn copper conducting. And now look what happens. You induce current. I can make you jump higher if I can move this. So this iron core in the primary solenoid is designed to keep the magnetic field pretty much in place rather than letting it go around. And here just look what happens when you induce current in this secondary coil. So the direction of the induced current is such that the induced magnetic field opposes the change of flux. As a result, this copper ring becomes like a small magnet because current is flowing in it, circular current. That small magnet has polarity opposite to the polarity of the magnet of this electromagnet. Opposite, all the time opposite, and you see that it jumps. And the same thing you can see with aluminum ring, much the same thing.
Polarity of opposite would be attracted to it, or?
Well, the polarity is in such a way to oppose, so that you're right, it should be the same polarity, so you have north with north, or south with south. It varies, of course, in time because the current here is AC current. But always you have the polarity here in such a way that you have a repulsive force. Now, what are the materials? What if instead of a metal ring, if we use insulator? What is going to happen with this insulator? Yeah, it's not going to jump. You are still going to have voltage induced here, but this voltage cannot drive current because the resistance of this insulator is very high, and no induced current, you're not going to have induced magnetic field, and nothing happens. What about a ring like this?
So for the insulator, would we just have to increase the voltage to overcome the resistance?
Oh yeah, if I increase the current here to some huge amount, eventually, well, theoretically, you're going to reach a situation in which the induced voltage is going to be sufficient to drive current here, and you're going to see smoke and so on. But we're talking about currents that we cannot even create here. It is not even going to be a reasonable thing to do, right? Because if you can drive current through this insulator, you can drive current also through the air. We're going to see sparking, and it's going to be an interesting situation. Okay, what about this? Right? No. What is going to happen if I put first the insulator and after that this aluminum ring? The same thing, it is just going to jump. Of course, no current here. What about, let's see if I can take you here.
Is the height reduced because of the insulator being on the bottom?
No, not exactly, no. So, voltage is induced in both of those, but the current only flows in the metal, and the insulator just stays there. It's just like a piece of, like an air gap. No, nothing substantial, but let me see if I can take you this way. Let's see, here are two aluminum rings. Jumps. This doesn't happen. Of course, I'm trying to trick you. What's happening here? Yeah.
Is it because that ring has a gap in it? So the current
Yeah,
can be.
well, I couldn't trick you. Okay. See, there is a gap, here. So voltage is induced here, but the induced current cannot flow because of this air gap. Okay.
We should have a question like that on the test.
Yeah, well, yeah, you're going to have questions like this, yes. So you're going to have a question like, if I don't forget, of course, but you're going to have a question like here, piece of insulator maybe. Is there induced voltage? The answer, yeah, there is induced voltage, but that voltage cannot drive current. And the same thing about, there is a question in the homework assignment about airplanes that is flying in Earth's magnetic field. Is there induced voltage between the two tips of the wings of the airplane? Yes, there is voltage there, but there is no closed circuit, so that voltage cannot drive current. Okay. Let me make sure that I'm not skipping something important. Actually, everything in this chapter is important. Now let's write a few formulas about energy. So you see that this metal ring jumped. So there was some energy that was transferred eventually from the power grid into this metal ring. And we want to quantify that energy. So in the textbook, there is no derivation of the formula for the amount of energy that is contained in this magnetic field. But the formula is written in analogy to the formula for energy of electric fields. So a few weeks back, we proved that the amount of energy stored in space where there is a electric field, the amount of energy per unit volume of space in space where the electric field is E is given by 1/2 electric permittivity of air or vacuum times the electric field E squared. This was the formula. So everywhere where you have electric field, so for example, if you create electric field just by rubbing some plastic object and creating static electric charge here, the space around that static electric charge is going to have electric field E. The amount of energy in that space around the charges, the static electric charges, is given with this expression. Of course, the further you go away from the source of the electric field, the weaker the electric field is going to be. So E is going to drop, and the amount of energy, the energy density is going to drop as you go farther away from the source. And we also looked at the case when the electric field doesn't drop as you go away from the source. This happens when you have a parallel plate capacitor. Two parallel plates, metal plates, large area plates, separated by some distance, and one of the plates charged with positive, the other one with negative electric charge. We proved that the electric field between the plates is uniform. It's pretty much the same everywhere around the plates. And we proved that amount of energy stored in the space between those two plates is given with the following formula. The energy stored in this parallel plate capacitor is equal to 1/2 the capacitance of the capacitor times the voltage between the plates squared. Right? Simple, nice formula for energy that you can store in a capacitor. Well, similar considerations yield the amount of energy stored in magnetic fields. So the analog of this formula for energy density looks like this, the magnetic analog. Energy per unit volume is equal to 1/2 the inverse of magnetic permeability of air or vacuum times magnetic field squared. So pretty much the same structure of the formula for energy density. So using this formula, for example, if you know the average strength of the magnetic field around the planet Earth, you can calculate how much energy is stored in that magnetic field. And you're going to get some substantial number just because the space around Earth that has magnetic field, non-zero magnetic field, although that magnetic field is weak, the space has large volume, and the result is going to be substantial amount of energy that is stored in that magnetic field. In a similar manner, when the magnetic field is uniform, and uniform magnetic field you have inside the solenoid, right? Inside the solenoid, the magnetic field is pretty much constant. And in that case, the total amount of energy stored in this solenoid with current in it, you need current to create that magnetic field. You can demonstrate that that total amount of energy stored in this solenoid with current is given with 1/2 the inductance of the solenoid, the self-inductance of the solenoid, times the current that is flowing through the solenoid squared. So those two formulas give you a tool to figure out how many joules of energy are stored in places where magnetic fields exist. Yeah.
Sorry, what did you say L was? The big L?
Here,
Yeah.
energy is 1/2 inductance times current that is flowing in the solenoid with that inductance squared. Okay, so what is left from this chapter is to describe the workings of a transformer. And this is not that difficult. A transformer is a simple device. Again, you have two coils. One of them is energized primary coil with certain number of turns in it. And the second is secondary coil that is not energized. So you have a situation like this. Here is the primary coil connected to AC voltage. So you have current, variable current in the primary coil, the number of turns in the primary coil and primary, and you have some RMS voltage V primary. RMS voltage or amplitude doesn't matter. And somewhere next to it, you have a secondary coil with number of turns and secondary. Well, if you want, you're going to induce voltage. You're going to induce voltage in this secondary coil, call that voltage V secondary. And if you close the circuit, of course, you're going to drive a current I secondary in this secondary coil. Now, look, the current initially is only flowing in the primary coil because only the primary coil is energized. But magnetic field created by this primary coil, eventually part of that magnetic field is going to enter the secondary coil, and it is going to induce voltage and current there. Now, you want all of the magnetic field created in the primary to reach the secondary coil. And you do that, you make it go to the secondary coil practically without losses by connecting the two solenoids, the two coils, with a ferromagnetic, with iron core. So here is a transformer like this. It is quite heavy, but you have primary coil right here, secondary coil here, and they are connected with this solid iron connection. No electrical connection. The iron core is just to drive the current, the magnetic flux. The magnetic flux shouldn't stray in space. The magnetic flux has the property that it prefers to go through iron or other ferromagnetic material. So the magnetic field stays concentrated through this iron and doesn't stay much around. As a result, whatever is the magnetic flux in the primary magnetic flux to a single turn, the same magnetic flux to the same turn through a single turn goes through the secondary coil. Now look, the induced voltage in the secondary coil, according to Faraday's law, it is equal to the magnetic flux that goes to the secondary divided by the time interval. So the change of magnetic flux per unit time, the rate of change. This is Faraday's law. But the magnetic flux to the secondary is number of turns in the secondary times the magnetic flux for one turn, like this. And there is minus sign again, that doesn't do much. But now look, this iron core makes sure that whatever magnetic field is created in the primary, that magnetic field with practically no losses reaches the secondary. You have this. And the result is that you can write this induced voltage in the secondary as, well, the number of turns is a fixed number, it gets out of the delta. So you have negative number of turns in the secondary multiplied by the rate. Well, secondary or primary doesn't matter, divided by the time interval. Exactly the same formula you can write for the voltage in the primary. So in the primary, you have an equilibrium between the voltage that is provided by the source and the self-induced back voltage. But the result is going to be some voltage that is going to be equal to the number of turns in the primary times the rate of change of magnetic flux in the primary divided by the time interval during which this change happens. So now take this and this equation and divide them, and you're going to get the following expression. So when you do the division, you get that the voltage in the secondary coil divided by the voltage in the primary. Well, this part and this part cancel out because the flux in the secondary and the flux in the primary are pretty much the same. So because of this cancellation, you get that the ratio of voltages is equal to the ratio of the number of turns. Yes. In other words, the voltage that is going to appear in the secondary coil is equal to the voltage that is in the primary coil times the ratio of the number of turns. Now, if this ratio is larger than 1, if the number of turns in the secondary coil is larger than the number of turns in the primary coil, you have a step-up transformer. The voltage in the secondary is going to be larger than the voltage in the primary. And this is what you use when you want to increase the voltage. For example, when you want to transport electric power from the power station that may be 100 miles away from the town, it can be shown that if you have higher voltage in this high tension power line, you're going to have smaller losses of energy. And this is why the electric power generated in the power station is increased with a step-up transformer, increased to thousands of volts. This thousands of volt electric power reaches down. There is a substation, usually outside town, where that voltage is reduced with a step-down transformer, usually to 72,000 volts. Those 72,000 volts go close to the house, and close to the house you have another step-down transformer that reduces the voltage from 72,000 volts to 120 volts, and you can use it. So this is the use of the transformer. Again, if the transformer is increasing or decreasing the voltage, depends upon how many turns you have in the secondary coil and what is the ratio practically between the number of turns in the secondary and the number of turns in the primary. So let's say that you have a step-up transformer. Let's say that the ratio of turns here is 1,000. In other words, let's say that the secondary coil has 1,000 times more turns than the primary. If the primary voltage that you put in, let's say, is 120 volts, the secondary coil is going to have voltage 120,000 volts. Well, you increase the voltage, but this doesn't mean that you get something from nothing. You increase the voltage in the secondary, but the current that you can draw in the secondary coil is going to be smaller than the current in the primary. So energy is not lost or created. So you want the amount of power, average power in the primary, to be equal to the average power in the secondary. Average power is a product of RMS voltage times RMS current. So average power in the primary is going to be voltage primary times current primary, while the average power in the secondary in a similar manner is going to be voltage secondary times current secondary. Well, this means that if you solve here for the current in the secondary, you're going to get that the current in the secondary is voltage primary divided by voltage secondary, all of this multiplied by current primary. But the ratio of voltages primary divided by secondary is right here. It is number of turns in primary divided by number of turns in secondary times current primary. So it is a similar expression like the voltage, but it is reversed. This means that if you have a step-up transformer, this ratio is going to be smaller than 1, and the amount of current that you can draw in the secondary coil is going to be reduced compared to the current that is flowing in the primary coil. So you gain voltage, but you lose current in the secondary coil. So this pretty much describes everything. It is a long chapter. The key in this chapter is Faraday's law of induction. Everything else follows from Faraday's law of induction. Let's see questions and remarks. If not, let's go to problem number 9 first from the homework assignment on chapter 22. Problem number 9. Actually, it is a practical problem with, that may be important for people that have medical professions in mind. Let's see where to solve this problem number 9. Here. Problem number 9. So you have MRI device, imaging device, and in order this MRI device to work, you have to put the patient in strong magnetic field. Well, you have strong magnetic field created by a solenoid that is just like this one, just bigger so that the patient can get inside the solenoid. And you produce 2 Tesla magnetic field inside the solenoid, and the patient is also inside. and largest surface of the body. So the cross-sectional area of the patient that is lying inside is, for my version, it is 0.034 square meters. So this is the cross-sectional area of the body, average, some average cross-sectional area of the body. Okay, the magnetic field 3 Tesla. So now let's say that, well, usually nowadays those solenoids are superconducting, but it doesn't matter if it is superconducting or normal solenoid. In order to create this 3 Tesla magnetic field, you have to drive strong currents in this solenoid. And suddenly you have power outage, and the magnetic field, the current stops, the magnetic field stops. If the magnetic field changes from 3 Tesla to 0 eventually, Faraday's law of induction says that voltage is going to be used in any loop, including in the patient's body, because patient body is also conducting. So the induced voltage in the patient body is going to be equal to the change of magnetic flux per unit time, the rate of change of magnetic flux. So the magnetic field goes from 3 Tesla to 0. Therefore, the magnetic flux that goes to the patient goes from whatever value it is to 0. And therefore, you have induced voltage in the patient's body. That induced voltage is going to drive current, and that current may fry the patient, may just kill him. So they're telling you that the human body can tolerate induced voltage that is of the order of 100th of a volt. If you induce higher voltage, the current is going to be strong enough to kill the patient. And the question is, well, how you have to put some circuit, some electronic circuit, so that if the power stops and the magnetic field goes from 3 to 0, it to go slow enough so that the induced voltage not to exceed what is the maximum amount of voltage that the patient can tolerate. Well, let's see. The initial voltage, the initial magnetic flux, when the current is flowing normally and you have 3 Tesla magnetic field, is the magnetic field multiplied by the area of the cross-section. This is the cross-sectional area of the patient. Right? The magnetic field is this way. The cross-sectional area has normal in the same direction. So in the formula that defines the flux, the magnetic flux, the cosine of the angle between the magnetic field and the normal to the area is 1. The angle is 0, cosine of 0 is 1, so I'm not writing it. So this is the initial flux. The final, so initial magnetic flux. The final magnetic flux, when the power stops, is 0. In other words, the change of magnetic flux is equal to magnetic field multiplied by the area. And the induced voltage, well, with minus sign, final minus initial, if you want, sign. The induced voltage in the patient is going to be equal to the change of flux, magnetic flux, divided by the time interval delta t. So we already determined delta phi. They tell us induced voltage shouldn't exceed 100th of a volt. How much time do you have to reduce the magnetic field from 3 to 0? Well, the time interval, delta t, is going to be equal to delta phi divided by the induced voltage that is allowed. And you have to plug into numbers here. So you're going to have magnetic field times area divided by the allowed induced voltage. So you have 3 Tesla multiplied by 0.034 square meters for my version and divided by 0.01. So whatever number you get from there, it is going to be a number like, what is it, 3 times, for my version, it is going to be 0.1 0.02 divided by 0.01 is something like 1.02 seconds, or 10.02, something of that nature. Do the arithmetic more carefully. You have one more zero right here. Or no, you don't have one more zero. So this is right. This is 10.2 seconds. So you have to have in this MRI device, you have to have a circuit that if the power stops, it reduces the magnetic field slowly. And it needs about 10 seconds, the magnetic field to go to 0. Okay, so any questions and remarks? If not, on Wednesday, we're going to continue with chapter 23. It is RCL circuits. That chapter is based on the discussion that we had so far. So everything is connected, unfortunately. Work on the homework problems, and if you remind me, I'm going to solve problem number 10 on Wednesday.